I'm Michio Yamada, Kyoto University. Okamoto-san told me to chair this morning session. So the first speaker with this session is Professor John Grue from University of Oslo. And his title is Nonlinear Surface Waves at Finite Depths with and without surface cover. So please.
Thank you very much. Good morning, everyone. First, I would like to thank Professor Konstantin for this invitation. Very much appreciated. And I would like to acknowledge my co-author or co-worker, Jostein Kolas, postdoc with me and very skilled with laboratory measurements. So amazing guy in the laboratory. So the motivation for this talk and this research was actually coming from the offshore wind industry. This is an international activity which is really for the future, and it's growing. And of course, wind turbines are being made offshore. And here in the UK, you have several wind mill farms. So this is the actually the high wind wind turbine of Statoil. So this is in deep water. We are in finite water depth here. But the main point of the research here was to find out what was the strongest kinematics. So we are talking about what is below the waves. And then eventually this research evolved, so then we are talking about what actually you see here. You can see this white capping, and you can see all these processes going on the sea surface, where what's going on below the water is contributing to a lot, and that is to the momentum fluxes through the water surface between the air and the water. And in the very last part of my talk, I will give some results from not myself, but from my research group, where they study the same processes when the waves interact with the ice, and with a fear that oil spill could also play a role. So this is now the motivation. So I will speak about three parts. First, the kinematics of the almost highest waves. I'm saying almost because it's like it's possible to make them a bit higher, but we'll discuss that a little bit. And then the main part two, will be about particle paths in the lab and the observed drift. So it took us a while to sort this out, so it's some points to discuss. And then I will, in the end, discuss the effect of a cover. That will be brief. I assume that the experiments had to come further, but it's preliminary results. So part one, kinematics of almost highest waves. So we wanted to look at here come some definitions. We wanted to look at what are the biggest waves in finite water depth, not theoretically, but in the lab. So it's a sketch of the wave tank on the blackboard there. It's not deep water, it's not shallow water, but it's in between, intermediate depth. And then you oscillate this wave paddle back and forth, and then when you increase the amplitude, you wonder what is wrong, because you cannot put more energy into the wave. It's different from deep water, because then it's easy to make very steep waves, but in finite water depth that's not easy at all. So then we have a layer of water depth h. The period is t, the same as at the wave paddle. It's a earlier in period, and we have the wave height. And of course now, so I just introduce, for definition, the non-dimensional period is useful, and the non-dimensional height. So we work with this. So then we do this experiment, and this is what we get. We get 22 water depths down in the wave tank. We get this image. And this is the wave height, or the wave profile in one point. So it's viewed by some camera, but it is in one point, and it's going up and down. So here comes the first wave, the second, and so on, and then it's more or less steady. It's more or less steady. So here the period is 8.75, the dimensionless period. The point is that we couldn't get more than 0.49 for the wave height. And we also had the maximum velocity, which we wanted to measure, 0.5. So now I wanted to connect this with what one could see in large scale. So how did the lab connect with what existed on measurements at sea? So then I went to the literature and got to this paper, this investigation by Nelson. And he was collecting a lot of data from what other people had been doing, Lemehot, for example. And he did experiments on the Great Barrier Reef himself. And what I did was to plot this non-dimensional wave height versus this parameter Fc. And Fc is simply the wave height times the period to the 5th power and the square root of that. So this is kind of the practice for people working on the sea. So our experiments are for Fc 160 and 330, so we are about here. And here are all the experiments he could collect more than 20 years ago. And you see here many branches. You see several branches. You see one branch here. And then you see an upper branch here. So we are in the long wave regime here. So these are the solitons. You can go up to more than 0.8. I think it's 0.83 something, maybe 0.87. But this is the lower branch. And we are here. We fit with the lower branch. So actually we fit quite well with what people have observed on the sea. So that is interesting. So I went through the paper by Nelson, and well, here is also an empirical curve. I have not seen that proved anywhere, but this is like a line they draw, which existed by that time. So I want to show you his experiments on the Great Barrier Reef. You can read his paper, but basically the reef is here. The water depth is, because of the tide, is less than 3 meters, goes up and down. And then he mounted four big poles, wave gauges on the reef. And you can see the distances here. The front of the reef is here. The reef is basically entirely flat, horizontal. So then he measured the waves at pole 1, pole 2, pole 3, and pole 4, and so on. So here are the results on pole 1. So then you can see that the water depth, the wave height can be up to 1, the same as the water depth. So then he went to pole 2. So now you see that his measurements, the points are moving down, some are moving below this line. And then pole 3. And then at pole 4, they are all at almost below the curve. And the process here is a breaking. What we had problem with in the lab is that the wave was breaking at the wave maker. So you increase the amplitude, you increase the stroke, and it's not working anymore. It doesn't put energy into the wave. So the breaking is a limiting factor. So there's a good news for those who make wind farms. You put your wind turbines away from the deep water, and then the breaking protects the wind farm. So that's one good message for the industry. Then there is another set of experiments by the research group of Babanin, and they actually measured wind waves in a lake. Very controlled experiments, random waves. And here they put, so this is the wildest set of experiments or measurements they had with the wildest wave height. So here they have this wave height of 0.55, and here you have the line of 0.44. And basically they find that waves above 0.44 were breaking. 1.4% of the waves had a wave height above 0.55. You can see some here, 2, 3. They've also found that waves below 0.44 could break. So his range is T prime above 4.5 and less than 9.7. So a little bit shorter waves than we have. And here is some literature which describes all these observations, where the breaking is the big limiting factor. Other people, like the Danish group here, have been able to have larger waves in the lab, so by some clever arrangement, but basically the conclusion from our study is that we couldn't get higher. So we could, of course, do it in a different way, but if you just switch on the wave maker, you are limited anyway by the breaking. So now we are going to discuss this data set. So we have wave 1 or peak 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are the peaks, and we are going to study more what is happening in these 6 or 5 large remaining waves, largest waves. So here is the what we see now in the lab close to the wave maker. So you see the stroke here. It's xi naught, which is the amplitude of the wave maker over the water depth. It's increasing from 5% to 0.37, and we are discussing a measurement with this amplitude. So that was the highest we could get and not have breaking. Those measurements where we could have the highest waves. You can see the breaking indicated by the light blue, and even stronger and stronger. And these were the non-breaking waves. And here you see some breaking still. So here is a breaking. So it's an illustration of this data set. So of course, then when we do these measurements, I'm returning to how we do that. We get in this case now the normalized horizontal velocity, and we can put up the streamlines. This is from the measurements for crest 10, and we can have the horizontal, the vertical velocity. It's rather symmetrical. And this is the third wave, which is unpolluted by, or maybe it's the cleanest wave. The wave height is 0.435, and here is the computation of the same. But with the computation, you can just compute much higher waves than what we measure. It's a good fit between the computation and this wave and the measured wave. So part 2, the particle paths and particle drift. So I will introduce this part by showing some images from the laboratory. So this is the lab. The green tank here is 25 meters long, and the experiments are being done here. The wave maker is up here. And we do the experiments before we have any reflection. So we don't have any interaction with the far end. You don't have any pressure gradient, for example. So here you see there's a lot of project in the lab. What is a typical recording device is all these cameras. So we all use cameras. We always use camera. And we are very good on health, safety, and environment. So when the laser is on, all have to wear laser glasses. So basically you see nothing. So if you remove the glasses, you can see the laser. On, you don't see the laser. That's the trick. So when we have a warning that the director is coming, we all have glasses on. All those who run the laser, they are the boss in the lab. They are really the boss and throw out people if it's some dangerous and so on. But what you see here is we use always laser light. And you can see the particles we are using. From silver particles, sometimes we crunch paint, depending on the application. And then we use a 2D technique. That's sufficient. 3D is cumbersome, takes a long time. So we always have a light sheet, and then we use the cameras to record the particle motion. Very simple. It's a visual technique. So, but then you can do it very accurately, so you can get a lot of information from the motion.
Excuse me, how wide is the tank?
Half a meter. Yeah. So then, the technique is particle tracking. So we do like many people here in the audience do. You track a particle. So it's exactly what you want to do with the equations. So you have particle image velocimeter, then you do ensemble averages. You use a lot of Fourier transform. It's a lot of programming with this. So now in this experiment, the field of view has height the same as the water depth, but of course the wave has some height, so we have to use two heights for the camera. So the number of pixels is the same as on your cameras. 1500 frames per second. So that means that we need to use many time windows. So it's a big, the experiment is repeated many times. So here we come to this white line. Can you see the white line here? So then the camera is full. So then you do the experiment again, and you take this window, and then the camera is full. The memory disk is full, and then you do it again. So you do this time window, and then this time window. And then you move the camera down, and then you do this time window, and this time window, and so you do 8 time windows. So 8 repetitions, 8 different experiments. It's very accurate. Same period, and recording 22 water depths upstream of the wave maker. So now the focus is on exactly what many of you do. What is a particle motion? So actually what we measure is this dx and dy in a time instant. So then actually we extract the velocities, but we measure this excursion. So now we integrate the excursion to find the path. So Jostein Kolås did all this. So here are some paths during one wave period. So it's the same period as a wave maker, the Eulerian period. So this is trough to trough, and now we are in the time range 6.51 to 7.76 seconds. So we have one pass here, and it's coming down and up here, then the period is over. So that is moving forward. Let's see. This is a guy here, so now it's a question. So this particle is moving backward. It wasn't so easy to see here. This is trough to trough. This is crest to crest. Kind of, it's like not so systematic. You have different excursion here and here, for example. So these are other samples. We have, like in the top, we have a forward drift. In the middle, backward drift. In the bottom, we have a forward drift again. So then when you start to record now the net displacement after one period, you have this line for crest to crest. You have this line from trough to trough. So it's different. So it's kind of what's going on here. Definitely we have positions where the drift is 0. Here and here, here and here. They are at different vertical positions. So it's like, doesn't look like any systematics here. And if you do it like in this phase of the wave or this phase of the wave, you get different results. Now this is with the Lagrangian period, where you follow the period at one position. You follow the period, you can do it's many loops, so you switch from the Eulerian to the Lagrangian. But then you also note that the Lagrangian period is different at the different positions. But here, now, the loops are complete. So what did we do? The Lagrangian period, crest to crest here, trough to trough mid, and crest to crest. Now the motion is the same. So I'm coming back to this. So the Stokes drift, some points about that. It contributes to the momentum and energy fluxes at the ocean surface, so it's very important in climate modeling. So in these models, the Stokes drift is expressed in terms of a vertex force, which is then integrated, and it contributes to the turbulent kinetic energy equation. And these wave effects in turn generate the Langmuir circulation, and you can find an update of this practice in this paper. And of course then the Stokes drift contributes, it's like the waves set up a drift which contributes to the circulation of the oceans. So then you have theories with that. So then you have Lagrangian theories for this wave current interaction. And then a different thing, we know that the return flows develop below a finite packet. So then if they have a drift and in the top of the wave, then you have a return flow below the wave packet, due to Longetigitz and Stewart, and you can also read the paper by McIntyre. I discussed this research with McIntyre recently. And then actually people measure the Stokes drift on the ocean. So Fabrice Ardouin, the French guy, and his group, they are actually measuring the Stokes drift on the ocean. So I'm measuring the Lagrangian drift. That is, by definition, it's a mean Eulerian drift plus a Stokes drift. So then it has been a debate, is it any Lagrangian drift or do they equal out each other? Actually we got some help in this when we were doing this research from a work by the American research group by Moni Smith, because they speculated what was going to the Stokes drift or the Lagrangian drift when the water depth was reduced. So could simply the shear at the bottom ruin everything. So then we thought that we need to clarify this because it was a conflict. So then one of the very visible effects is the effect of the bottom boundary layer. That is a well-known thing, which was, I believe, studied systematically for the first time, no, the order 100 years ago or 70 years ago by Bagnall. So he was interested in the drift of sand particles below the waves. So he did a measurement in the wave tank. So this is the wave propagation direction. So then he put some dye, vertical, very clever experiment, and notice that the dye drifted forward above the bottom and backward in the remaining part of the water column. So this is the Lagrangian drift. It's a big effect of the wave-induced boundary layer streaming here. So that is going forward. And we find that you have the same thing at the surface. Just a short note about some formulas, very brief, because I want to calculate the particle drift velocity. So this is the linear velocity potential, assuming small waves, and here is a term which accounts for a back flow. It's linear, it's constant, the flow is constant. And then in non-dimensional terms, and I then can find the fluid velocity, and I can find the time averaged horizontal particle velocity to second order. This is my point. I can do the same thing with the Lagrangian period, the excess period. It is the same expression. And then I can find this U2 by mass conservation. I assume that there is no net mass flux. I'm going to verify it experimentally. And then a point is at the Lagrangian excess period, and the mean drift velocity have the same formulas, have the same functional relationship as function of the vertical coordinate. So now I'm returning to the PTV. In two time windows, one with this in this time interval, and time window 2 in this time interval. So we identify 120 million particles in each time window, and from these we construct the path fragments. So 0.2 million particles for the basis of the path in time windows 1 and 2, and we use interpolation and smoothing. So then for each loop, each of these loops, we integrate the particle path backward in time and forward in time. So then we shift it and minimize this distance. And from this we calculate the Lagrangian period and the drift distances, the horizontal and vertical. And we introduce the average vertical coordinate of one loop, which actually nicely fits between 0 and -1. So that is actually quite accurate. We do 75 different initial times or phases, and 500 points along the vertical, and totally 40,000 combinations in each time windows. And then here are results for the Lagrangian period and drift velocity. So this is in time window 1. This looks. This is what we get. The blue are all the experiments, but you see, you have a collapse of the data, which is like very gratifying. So you have basically one curve of all these points. The yellow is the second order theory, and the red is a strongly nonlinear theory of Fenton, so Fourier series. What you notice here is that you have this positive excess period at the bottom, above the bottom, and you have a very much stronger excess period at the top compared to the theories. Zero is here. You have the excess period is zero at two different points in the vertical. So let's move to the drift velocity. Oh no, this is a same function for the second time window. So not exactly the same, but very similar. Again, a collapse of the data. This is now the drift, the Lagrangian drift velocity in time window 1. It has about the same functional relationship. The yellow line is the same as for the excess period, and the red is a little bit different. So here is the experimental Eulerian mean velocity, and the Stokes drift is the difference between these two. So we can't get higher up than the trough, of course. In the theory, this is now the Eulerian drift velocity, mean velocity. So this is time we know 2, basically the same. So we have just one result. So it's not much results to talk about, but we have collapse of the data. We can evaluate the volume flux. That is, so this is in time window 1, 0.2 times 10 to the minus 3. So if you look to the speeds here, it's 1% basically of the speeds here, very small speeds. So the mass flux is 0. Time window 2, the same. We can integrate the excess period. That is also 0 at in the average, approximately. So then we can calculate the Eulerian mean velocity. You can see it here. This is 1.2 millimeter above the bottom. This is the blue. So then you have like a strong forward Eulerian mean velocity. A little bit further up, the red, then you have a negative mean Eulerian velocity. And that is almost constant because this is right below the surface. You can see in the beginning of the wave it's positive, and then it goes to a steady state. We cannot measure the boundary layer, what's happening in the boundary layer. We are measuring right outside the boundary layer. And we clearly see the effect of the streaming. Yeah. Yet kind of an easier understanding of these processes when you look to the vertical gradient. So I've just taken the vertical derivative of the drift velocity. So here are the theories. The yellow, the Stokes, the second order theory, and the red, the nonlinear theory, and the blue is the experiment. So you see that above minus 0.9 and below minus 0.2, basically you have the same physics in both theories and experiments. You kind of have exactly the same thing. But at the bottom, you have the effect of the streaming. So you have this strong shear. And at the top, you have also the strong shear. So this points to the effect of the boundary layer at the top. So this is the period. We're taking the derivative of some millions of, some thousands of points. We have some wiggles here. So this illustrates some inaccuracy of the experiments. But basically, we have the same physics here and not at the top and not at the bottom. And for the second time window for the period, and the same for the drift velocity. Same physics in the core of the water column, but at the top and bottom you have a different physics. So then you can start to compare more numerically. So we have this experiment and the implicit theories. So you have the second order, which is kind of what all this research is based on. I mean, the Stokes drift is based on second order theory. And then you have the nonlinear theory, and then you have the measurements. So you see that you have a much stronger Lagrangian drift at the top of the water column. It's almost a double. And regarding the shear, it is 4 to 5 times bigger than the second order theory, more than double than nonlinear theory. But this is the shear is really 4 to 5 times bigger than what is exists in the literature or in the practice. So then we can also evaluate the vertical velocity in time window 1 for check. So of course we have some oscillations. It's not exactly 0, but it's 1 order of magnitude smaller than the horizontal velocities, time window 2. So then part 3, effect of a cover. This is brief because the experiments have not made much progress. So waves and ice applications, and I'm citing a work by Jean Rabault et al. In our research group. So what is a worry here is that oil spill potentially can drift under the ice. They wanted to measure that. It's not so and model it. So here is the waves, and then this is the frequencies period they investigated. So now the waves are more deep water waves. The wave slope is the same, about the same. But they do the experiments in a different way. So they have they assume the Stokes drift in this fashion, and they have a quadratic return flow profile in the lab, because they are running the experiment over a longer period. And they are comparing to theories which are described here. So then the point is to add an ice cover, and they do it by having a latex sheet on the top and measure what's going on below. And they encounter some trouble with velocity fluctuations, which they have to subtract. So they do a correction, which we didn't do, but they do it and find a reason for doing it. So here are the results without cover. The blue are the measurements. The solid red line is Stokes drift with recirculation. And this is without any correction for the backflow. So this is for this noise. So this is with correction. So they are quite happy with this result, but say that this is just preliminary. So what happens now if they do it with cover? Then it's a green line, which is like the theoretical profile. So this is with cover with no correction, and this is with cover with the correction. The research will regard this as still unpublished, or they published it in the conference, but they want to work on improving the quality. But what you can read here is that the forward drift is stronger with cover than without cover. That is what we can read. I've come to the conclusions. Number one, braking effects limit the height of finite depth waves on a flat bottom. If you have a non-flat bottom, then the story can be very different. The drift velocity and excess Lagrangian wave period have similar functional relationships with the average vertical position of the particle path, independent of the wave phase. The streaming velocities in the boundary layers below the wave surface and above the fluid bottom enhance both UL and the excess period right below the wave surface and above the bottom. It's very different from inviscid theory, or inviscid theory cannot capture it. The drift velocity and excess period are positive below the surface and above the bottom, and negative in the middle of the water column. The shares of UL and delta T compare well to the nonlinear Fenton method and the second order theory for the core of the water column. There is no mass flux of the periodic experimental waves and no pressure gradient. The average elevation within the wave trend is unaltered by the wave motion. And close to the surface, the measured shear becomes much more than twice that obtained by the Fenton method, which again is approximately twice that of the second order theory. The Stokes drift is significantly higher than what is commonly represented in wave current interaction models, where the boundary layer streaming should be incorporated. The wave-induced drift under ice shows the same tendency, but the surface cover enhances the drift below the cover, below the ice. So there is more information in these three papers. So that's all. Thank you very much.
Any questions or comments?
Could you say what the paddle motion was, please?
That's a sign, just a sign.
Fine. So you had no second order correction in there?
No. Just wanted to do it as simple as possible. So we have some small parasitic waves in the, yeah, 8% of the wave height, yeah.
A comment on near the bed. Quite a lot of work was done in wave current interactions in the early 2000s, trying to get the shape that you have. And none of the turbulence models fitted it for the kinematics.
They did it?
They didn't.
No.
They all failed. They all cut it short, so you never get that bump that you get.
Yeah, but I don't think that turbulence models can help at all, because this is like the streaming. At least the first step you can do is laminar. Yeah.
For a slightly different problem. This is where, if you take the Grunewald and Klopman paper, where they produced the profiles that I showed yesterday, that uses a turbulence model. And if you then take that profile, which was measured, and you're only doing it to first order, not second order, which you're dealing with, the first order interaction could not cope using a turbulence model with that bump that you have. And it's never been satisfactorily resolved. What is you we could have a conference on your paper.
Okay, thank you. This is, if I return now to the first slide here, so see, it's heavy. It's coming here. You can actually see this effect immediately here. Can you see it? So you have a positive velocity below each wave crest. And that's the first you see, actually. But we have tried, we cannot measure the boundary layer. that you can measure the drift, the streaming outside. But I was most surprised I think this result here is maybe the most unexpected, that you have the same thing as the surface. I mean, Longetigid has done a theory for it, but Monismith corrected me. He said you cannot use Longetigins because he assumes a very small wave amplitude. But look at this share here. I think nobody has modeled it.
Some things like this can happen even in the lower order kinematics, not in the second order drift that you have. And it's often not looked at because the present wave theories work for us when you need them to work best, which is at the surface. So everything's a perturbation around the mean water level. And even if you have a laser, you cannot pick that up. But you've got PIV, and you see it on PIV testing.
And you can go right up to 0 here. Yeah. So this is maybe one of the most amazing dimensions. But today we have fully nonlinear theories and so on, so it's possible to at least calculate it. But I think this is, I want to see a calculation of this share here. It's very systematic. And even with the period, did you believe that?
The other thing that's surprising is how quickly this sets itself up.
Yes.
You wouldn't expect that, but it seems to start almost immediately, doesn't it?
It comes immediately, yes.
All right, okay. I guess in some sense my question has been asked, but have you compared to the streaming solution in Longetigins? Because he does develop some sort of expression for that backflow, and even near
Say it once more, compared to
the Longetigins streaming solution in 53, that in fact he developed some expressions for that forward flow near the base. Is there some comparison that can be done?
Yes, it's written in the paper. It's much smaller.
Right.
Much smaller. Yeah. Much smaller. We compare, but again, so when we tested this for JFM, so the referee said you cannot use that theory because it assumes small amplitude. Here the amplitudes are the maximum.
Right, but in some
so it's if you are gentle, you compare the velocities, you don't plug in the frequency and the amplitude, then you're quite off. If you do the velocities and do the same rewrite Longetigins velocities, you are kind of in the same order of magnitude. So we have compared, yes.
No, okay.
Yes.
One follow-up question, and your effect, does that scale with amplitude in a way you understand? As in when the steepness goes up, does this discrepancy, is it the amplitude squared effect, or does it
This is u squared, yes. This is the velocity squared. This is the amplitude squared.
The discrepancy also.
We have just one amplitude, the maximum. Yeah. But you see the answer to this. Here is a second order theory, the implicit. So you have the same thing here. So it's like so this is now the drift. You have the same thing. Can you see that here, all the way up here? But then you have different behavior. But basically, you have the same physics. So you can use a second order theory in the middle of the column, but not on the top and bottom. So that is kind of a very simple result. And this is for the maximum amplitude.
Yes.
Can you put a current in your wave tank?
No, we cannot do that in the facility we have. So my colleagues are developing a new wave tank, and they want to have just winds and current in addition. So hopefully, maybe sometime in the future.
Because I mean, it's a question when you set up your wave, when you look at these things, I mean, other than the boundary layer, should there be do you generate the current just when you know, when you do this? Does it it's a naive question. So you have your wave tank, you start with your paddle. Do you generate some kind of a current?
No, no, not at all. This is the point.
How do you know?
Yeah, the wave generates a backflow. So here is the volume flux. You calculate now you follow the all loops. You have 40,000 particle loops in any phase, in 2 time windows, the whole water column. And you have no net mass flux. You have no change in the water level. And you have no pressure gradient. It's very clean. You have no net excess period. So when I started the lab, the idea for the lab was 30 years ago. More than that. I threw out all the current devices because I don't believe you can have such an accuracy. This is very accurate experiments. And I am very amazed, so I was very happy to interact with Jostein Kolas, who is such a brilliant experimentalist. So we work together with this, and the accuracy is one of my worries. I think one of the conflicts that Monesmith and his group communicated was like, is it this or is it that? So the accuracy is a big issue, and if you add a current, well, I'm not sure if you can get such clean results, but hopefully some people can do it.
Can we check that your waves are potential? Maybe there is vorticity near the free boundary.
Yeah. Of course, that's the point. Here, of course, that's the point. I wanted to learn from the experiment what can we expect? What are the biggest waves, and then what is happening below these waves? So here you see that this is not inviscid at all, and this is not inviscid. But this shear is driven, this is an inviscid shear, but it's driven by some process in the boundary layer. And it's driven by the viscosity in the boundary layer, but this shear is inviscid. Because it's like the streaming. The streaming effect is extremely important. And when you, so when you go to like the ocean or in real waves, the boundary layers are much bigger. So this is, I mean, this shear here you should have like in the climate models, because you have it in the ocean, definitely, but it's not modeled. Some work to do.
So if you cover your wave tank, does that upper part diminish somehow or not?
Yeah, I wanted to show you these results because so here, if you have a cover, no cover, you have a fit with this theoretical profile, and they account for a backflow which is quadratic. So it's a different experiment that we did because I constant backflow. It's constant use, basically. And then when you do a cover, you enhances you lower the shear, but you have the effect further down in the wave column. You see the difference?
Yeah, but I was also asking cover in two different ways. I mean, you can think of cover, right, as ice sheet cover and cover of like not touching the water, but on top maybe, air circulation, whatever, near the
Okay.
surface.
I don't know. The only answer I have to this, is the experiments on the wave height by Babanin et al. It's coming. So heavy data. Here. In these experiments, they measured the wave height in a wind of 20 meters per second. But they measured the statistics. But I was after, so how high waves can they get? Basically, they get the same as in this experiment. So it's regarding the height, it's about the same thing. But regarding the shear, no idea.
Do you have any other questions? No? If no questions, let's thank him again.
Thank you.